In this next module, I'm going to talk about multiple linear regression. This is when we're now going to add multiple predictors to our regression model. This allows us to do all kinds of wonderful things like improve our predictions and statistically adjust for confounders. Multiple linear regression just means that you're adding more than one predictor to the model. So the right side of our regression equation is now going to get bigger. It's going to look something like this. So this now, our expected value of y, we can predict is equal to an intercept plus a slope corresponding to one predictor variable, another slope corresponding to another predictor variables, maybe even a third variable in the model. So we can put multiple variables in the model. Those predictors can be continuous variables, they can be binary variables, they can be categorical variables. We'll talk more about that in the next module. Each regression coefficient, the way that we interpret it is, it's the amount of change in the outcome variable that would be expected per 1 unit change in the predictor if all other variables in the model were held constant. So it's trying to get at the independent effects of, say, x. If you hold w and z here constant, what's the independent effect of x? What's the slope for x once you've held everything else in the model constant? That's the idea, and I'm going to kind of try to illustrate that concept now. There are many functions of multivariate analysis. So one of them is that it allows you to control for confounders. So you can put potential confounders in the model so that you can try to gauge the independent effect of the predictors you're interested in after adjusting for, after controlling for confounders. You're going to be able to isolate better the effect of the predictor you care about. Putting multiple variables in the regression equation allows you also to improve your predictions. So now instead of saying it's our political bent that predicts whether or not we like Obama, maybe there are other variables I can come up with that also help improve that prediction beyond political bent. Are there other things that predict who's going to like Obama? Another thing that you can do in a multivariate analysis is test for interactions. I'm actually not going to talk about interactions in any detail this week. I'm going to give this a lot of time next week. I sort of alluded to interactions in week 6, so you may be familiar with the concept, but it's something that you can easily test for in the multivariate regression analysis context. Again, I'm going to get to that next week. In this module, I'm going to work on the first two of these, controlling for confounders and improving predictions. So starting with the first one, how does multivariate analysis, how can it be used to control for confounding? I'm just going to illustrate this with an example. So let's start with the hypothetical data that I had on vitamin D levels and cognitive function. I'm going to use the hypothetical data set that had the strongest association between those two things, the one that had the slope of 1.5 per 10 nanomoles per liter. Here's the regression equation. We already fitted the best fit line here. This is the simple linear regression equation. The intercept was 20. The slope here again is 1.5. Of course, I made up these data, so I get to build anything into the data set that I want to. So I built in a confounder here. And it makes sense that this particular variable would actually be a confounder here. So what if age is a confounder here? So we're seeing a relationship in the data set between vitamin D levels and poor cognition. There's a real relationship in this data set. I know there's a real relationship because I built it in. But what if that relationship was coming through confounding with age? Remember, as you age, it's definitely true that your cognition, your cognitive function goes down. That's true for everyone. It's also true that as you age, you tend to have lower vitamin D levels. So as you get older, your nutrition isn't as good. That would affect your vitamin D. You also might be less likely to do exercise and go outside to do exercise and just be outside in general. All of those things result in older people having lower vitamin D. So you can imagine a scenario where you're seeing a relationship. If you just look at vitamin D and cognitive function, you might see a relationship there, but it could be driven purely by the fact that older men both have lower vitamin D and they have poorer cognition. So it might not be that vitamin D is causing the poorer cognition. It might just be the fact that vitamin D, poorer cognition, and age, older age, tend to cluster. Well, we can test for this. We can adjust for age simply by putting age into our regression model. Our outcome variable is still the cognitive function test, the DSST score. We're still going to have an intercept, but now in addition to the slope for vitamin D, we're going to add in a slope for age. If I have two slopes, what I'm actually doing is fitting now not a line, but I'm fitting a plane. And I can try, it's again always great to graph things, and I'm going to try here to graph this. It gets very hard to graph things for multivariate regression because you can kind of graph a plane, okay, but anything beyond a plane I can't really graph. But for two variables, again, we're dealing with something in 3 dimensions. Here's my 3-dimensional plot, my attempt to plot this. Of course, with 3-dimensional plots, what you're seeing completely depends on the angle that you look at, but I've tried to choose something that's illustrative here. What you're seeing is that vitamin D levels, that's your x-axis variable, your cognitive score is the y-axis variable, and age in this plot is the z variable. That's the one that's kind of going into your computer screen. So again, this is supposed to be 3-dimensional. What you can notice is that when in this particular angle, when I'm focusing on age is in the picture, but I'm focusing on the relationship between vitamin D and cognitive function, it no longer looks like there's much of a strong relationship there, right? It kind of looks like a random scatter. Compare that to when I kind of churn this 3-dimensional plot and put age on the x-axis and vitamin D on the z-axis. So now vitamin D is kind of going into your computer screen so you can see it less. And I'm kind of trying to isolate here the effect of age and cognitive score. Now you can see this strong relationship. As age goes up, cognitive score goes down. So based on the 3-dimensional pictures, it looks like there's a stronger effect for age here than for vitamin D. We can actually fit a plane here rather than a line. That's what our model is doing. We're fitting a plane rather than a line. Our plane is defined by 2 slopes. One slope for vitamin D and one slope for age. And what you're seeing here, that, for example, what you're seeing, these kind of vertical diagonal lines, that's the slope for age. Notice here that there's a slope for age at every different vitamin D level. Of course, the slope for age is the same at any vitamin D level. So for example, at a vitamin D level of, this is something like 60, here's the slope for age. Here's the relationship between age and cognitive function. There's a pretty strong positive relationship. As age goes up, cognitive function really goes up strongly. Contrast that to the slopes for vitamin D. Those are the more horizontal lines here. So these horizontal lines represent, this is the slope for vitamin D, the relationship between vitamin D and cognitive function at any given age. For example, if we take the age about 55 right here, there's a particular slope between vitamin D level and cognitive function. The slope is constant. The slope between vitamin D and cognitive function doesn't depend on the age, but we've isolated the effect of age because we're talking about the slope at any particular age, and we're assuming that that slope is the same at different ages. So we've isolated the effect of vitamin D in that way. You can see that the slope for vitamin D here is almost perfectly flat. It's almost 0, suggesting that the relationship between vitamin D and cognitive function is basically 0 once we account for age. If we're talking about a whole group of just 55-year-olds, there doesn't appear to be any relationship left for vitamin D and cognitive function. That's the idea here. We fit this plane and we see that the slope for vitamin D is almost 0, whereas the slope for age is very strong. Here's the computer output that corresponds to the model that corresponds to the picture that I just showed you. So I just showed you sort of the visual picture of this, and here's the actual fitted model that I've run in a computer. Again, you have to learn to kind of weed through computer output like this. What we're interested in are the parameter estimates. That's our intercept and our betas, our slopes. That's what the model estimates, as pictured on the graphic on the previous slide. We're also interested in the p-values that tell us whether or not those slopes are statistically significant or not. The standard error here and the t-value directly combine with the effect size to give us the p-value, so I most care here about the actual size of the effect, the parameter, and the p-value. The standard error and the t-value are really just useful for getting me to the p-value. So I am going to probably report in my paper, if I were to write a paper about this, the betas and the p-values. Here's our final model. Our outcome variable is DSS score. Our intercept is 53. The slope for age is -0.46. The slope for vitamin D is +0.039. Remember that the slope for vitamin D, when we didn't put age in the model, in the simple linear regression was 1.5. So we've now gone all the way from 1.5 per 10 nanomoles per liter, which was a pretty big effect or modest effect, down to 0.039, which is essentially 0. This is highly non-significant. Our p-value is 0.9. There's no evidence here that this is different than 0. And the magnitude of our effect of the slope is very close to 0. On the other hand, for age, the slope for age is negative 0.46. It's highly statistically significant. This is indicating that every 1 year increase in age is correlated with a half-point decrease in the DSST score. That's a pretty steep decline. Here again is written out the equation of the best fit plane. The best fit plane here is, again, 53 was the intercept plus 0.039 times the vitamin D in 10 nanomoles per liter minus 0.46 times age in years. That's our final equation. And you can see, again, that there isn't much effect left for vitamin D. Essentially all of the relationship we were seeing between vitamin D and DSST score can be explained by age, due to confounding by age. We can say there is no independent effect of vitamin D after accounting for age. There's nothing left over in this case. Now, a lot of times confounding is not going to be this strong. This is a made-up example, so I built in essentially complete confounding by age. Real examples are going to be a little bit more subtle. The effect may not completely disappear once you control for confounding. It might just be attenuated. But in this case, we're basically down to a slope of 0. All of the effect that we observed between vitamin D and cognitive function was completely due to confounding by age in this example. The evidence of confounding is in the beta coefficients. So the way that you test for confounding is you calculate the unadjusted beta, which here was 1.5 per 10 nanomoles per liter. Then you calculate the adjusted beta, adjusted for the potential confounders, in this case age. When we do that adjustment here, it goes down, our beta goes down to almost 0.039 per 10 nanomoles per liter. The evidence of confounding is in the difference between the unadjusted and the adjusted beta. If there is, the rule of thumb that people use is if there's a more than a 10% change from the unadjusted to the adjusted beta, and that 10% change could be an increase as well as a decrease. It doesn't always have to be an attenuation, although that's more common. If there's more than a 10% change, we usually would call that confounding. Notice in this case, there's a 97.4% change from the unadjusted to the age-adjusted beta. So there's, almost all of the effect for vitamin D was due to confounding by age. Again, the rule of thumb that you can use, and it's a rule of thumb, so it's not a perfect rule, but just kind of as a guide, if that beta changes by more than 10% when you put the confounder in the model, then you would consider it a confounder, and often that means you might want to consider keeping it in your model to account for that confounder, to adjust for it. Notice that I am not judging confounders by their effect on p-values. So you want to look at the betas to judge whether or not something's a confounder. You don't want to look at the p-values. You might be tempted in this particular example to say, oh, well, vitamin D had a significant relationship with cognitive function before I put age into the model. When I put age into the model, that significant effect disappeared. Therefore, I've got a confounder. But don't use the p-value like that, because sometimes you'll have confounders that aren't going to be strong enough to change the p-value from something significant to something non-significant. There's lots of things that, as we've talked about, impact the p-value beyond effect size as well. So you really want to judge confounding simply by looking at how it changes the effect size, how it changes the slope. So ignore what it does to the p-values. In this case, it happens to take the p-value from significant to non-significant, but that won't always be the case.